everyone, this video I'll explain a coffee cup calorimeter based off of reaction, and similar to the question we explained during the lecture. And then at the end, I recognize some of you do have some questions regarding towards it. Okay, so then that's why I'm making this video to clarify and also give you a different example question, so then you see what other angle we can ask you about this question. Okay, so now let me share my screen, so then let's look into it. Okay, so if you look at this question, okay, so very similar to the one we did. Okay, so say 100 ml sample of 0.3 molar of sodium hydroxide is mixed with 100 ml sample of 0.3 molar of nitric acid. Okay, so you go, okay, I have a coffee cup calorimeter. I'm gonna try to draw it real quick. Okay, so over here I have my thermometer. Okay, so my thermometer is measuring temperature. Okay, so now think about this. You put those two samples together. Okay, so just say that at the base over here. Okay, and the acid is over here. Okay, so then I have 100 of each. Okay, 100 ml of that base and 100 ml of that acid. Okay, and then again, we have to realize in the 100 ml of the base, just think about it, majority is what? Is water. Okay, so and then again, is it easy to really know what's the temperature for the sodium hydroxide and nitric acid? And then after they react, think about it. After they react, are they still gonna be there? What happens after they react with each other? Okay, so then think about that, then we probably realize we have to write out our balance equation. Okay, if you have sodium hydroxide and then put in with nitric acid, we're gonna have, since it's acid-base reaction, we're gonna have salt and water. Okay, so then you will have sodium nitrate plus with water. Okay, so and then it's 1:1 ratio. Okay, so and then clearly we recognize the stoichiometrically when they complete with they react with each other is what 1:1 mole. Okay, and then you also recognize from the given information, right? We can easily find out moles of each. Okay, moles of the base and moles of the acid. Okay, so since the value is the same, so which means they will have the same amount of moles, which also tells us they will complete react with each other. Okay, and then nothing left after the reaction. Then after the reaction, what do we have? We'll have that salt and water in my solution. Okay, so again, we don't have all of the information for my reactants and products, so therefore it's not easy to gather information for my reaction. Okay, so then that's what I also keep on saying, right? So it's not easy, but what can we do? What can we do is that we can find information about the surrounding. Okay, so what's our surrounding? Surrounding is this majority, again, as I mentioned, that's the solvent, which is water. Okay, so that water is not the water from your reaction. That water is the water in your solvent. Okay, so as your solvent. Okay, so then that's the water we're talking about. Okay, so that water, look, when you measure temperature, you're actually measuring the temperature for the water. Okay, so just say initially the temperature is what? When you put them together is for your water, which are your solvent, is at 35 degrees Celsius. Okay, and then after the reaction happens, right? What happens? So after you put the both react, they're gonna react. After the reaction, the temperature went up. Okay, went up. The final temperature, again, you're really just measuring the temperature for the solvent, that water. Okay, so that's our surrounding. Okay, so that's 37. Okay, so again, as I said, right? So basically, you're thinking, okay, if my water, which is the solvent, okay, is our surrounding, okay, so then the heat of the surrounding, we simplify. Okay, so we did assumptions. You can read through the assumptions, right? So then the heat just equals to the solution. The solution mostly just water. So then we can just use information for water. Okay, and then look, assume the density of heat is just the same as water. Okay, so then also the question might tell you that. Okay, so that's what I have again. Heat of water will have a relationship with my reaction is what? The negative relationship, in the sense of, right, one's releasing, the other one is absorbing. Okay, so then that's for that. And then for the negative sign, is only there, or is there to tell us the opposite relationship between the heat of my surrounding, which is water, and the heat of my reaction. That's all. Okay, so the negative sign can be on the other side or not. Okay, and this is also, I believe you recognize, right? So heat of the water plus heat of the reaction should equal to 0 if you reorganize the equation comes to this point anyway. Okay, so then that's for that. So now you go, okay, I can calculate heat of my water. Okay, I need to use the mass of water multiply specific heat capacity for water times the temperature change for water. Okay, so then the mass of water, you go, I don't know. But then the question is giving us, right? We put those two solutions together as you just analyze the situation, right? So majority is water, you put those together. My total volume is 200. Okay, so that's gonna be 200 Okay, and then that's volume, but we want to know mass. Since we treat it as water, we know the density for water is 1. Okay, so that will be times 1 gram per ml. So then the mass will be 200 grams. Okay, so then that's the information we can use now. Okay, so 200 grams multiply specific heat capacity is 4.14 joule per gram degree Celsius. Temperature change is 37 minus 35. Okay, so then let's do a quick calculation. I also need to do the calculation. Okay, so please, if you're watching, let's do the calculation together. Okay, so 200 times 4.184 times 2. Okay, so then that's 1673.6 joules. Also double check your units, right? That grams got cancelled out, degree Celsius got cancelled out. That's my heat for water, which equals to that many joules. Okay, we also understand the question is asking us actually about what? It's actually about determining delta H. You go, oh, how do I know delta H? But remember, we're talking about coffee cup calorimeter. So delta H for the reaction just equals to Q, right? Okay, at constant pressure. Okay, so then we can just calculate Q of the reaction. But you also need to recognize it's asking us to calculate in the units of kilojoule per mole of sodium hydroxide. Okay? Before we get to per mole sodium hydroxide, let's just calculate kilojoules based on what we have at this moment. Okay, so then let's do that first. Okay, so again, that's, well, the heat of the water equals to that many joules, and then we know my heat of my reaction just equals to negative heat of water will be negative 1673 joules. Okay, so then that's what happens. Then you go, okay, so that's joules. I can turn that into kilojoules easily. Okay, so then heat of my reaction equals to negative 1.6736 kilojoule, right? I divided by 1,000. I hope we're all clear how to convert joule to kilojoule. Okay, so then that's kilojoules based off my reaction itself coming from what? 100 ml sample of 0.3 molar, 100 ml of 0.3 molar of that. Okay, so again, as I said, we can easily calculate how many moles we're having this much heat based off above. Okay, so the question is asking about sodium hydroxide. So let's calculate moles of sodium hydroxide. Okay, so we have 100 ml times 0.3 molar, which is mole per liter. Okay, you do this calculation, we clearly see, right? That's now per mole, right? Unit doesn't really completely cancel, so we need to do the conversion. So that 1 liter is 1,000 ml. Okay, so I do this, I'll get 0.03 moles of sodium hydroxide. Okay, so then therefore, this information we just get is that based off 0.03 moles of sodium hydroxide, it's going to release 1.6736 kilojoules of heat. But if you want to know per mole, based off per mole of sodium hydroxide, what do we do? Very similar to the question we did in the lecture at bomb calorimeter, that one per mole, so then you just use this heat, negative 1.6736 kilojoule per mole, then we need to divide 0.03 moles of sodium hydroxide, because at this moment, that's what the relationship. Okay, so after the calculation, you'll be able to get to per mole. So let's continue do the calculation. Okay, so after I do the calculation, I got negative 55.8 kilojoule per mole of that sodium hydroxide. Okay, so then that's what my calculation come out as. Okay, so that of course depends on, right, how many specifics, or if you're using 4.18, so then 1/8, so then the answer might be slightly different, but again, the logic is like this. Okay, so then we just calculated delta H, right? We know delta H equals to Q, and unit wise is kilojoule per mole. So now we just calculated if we have 1 mole of sodium hydroxide reacting with 1 mole of that nitric acid, then this, how much heat it's going to release, is 55.8 kilojoules. Okay, so then that's what this question is about. Very similar to the one we did during the lecture, but then I just want you to realize again that water we were calculating for, as I already mentioned during lecture, and so that's the solvent. It's not the water generated from the reaction. That water is not much. Okay? And then again, majority, right, the surrounding you're trying to measure is that actually the solvent water. Okay, so then that's just how you can think about this type of question. Okay, so then the other hint I also want to quickly give you is that, look at this, right? So yes, I have been giving you the same moles, which means 1-to-1 ratio perfect, because my balance equation is 1:1:1:1:1 mole. Okay, so then they're gonna react with each other stoichiometrically completely. Okay, so then that's what that situation. But what if I give you a different number of moles? Then that question has a limiting reagent, and then that's something you also need to be able to take into consideration. If I don't have the same moles to start off with, right, the one with less, which means it's going to lead to the less amount of product, so then that's your limiting reagent, and then that's what hinders the reaction. So then you have to calculate based off that limiting reagent. Okay, so that's also something I want you to, right, so think about. Okay, so also, right, based on given info, sometimes you need to take into consideration for limiting reagent. For our question, again, they completely react with each other, so that was the situation. Okay, so that's for that. Okay, and then just to further clarify, okay, so what if I have a reaction like this? Okay, so look at this, I have silver nitrate, I have sodium chloride, I have a salt, which the precipitate. Okay, so silver chloride, so I have a precipitation reaction. Then I have sodium nitrate. Okay, so then that's what I have. Okay, so if you look at this, right, you go, oh, what do I do? Right? What do you do? It's very similar to the acid-base reaction. Very similar. You are putting all of this into the coffee cup calorimeter. What are you trying to measure? We're still measuring information for water. Okay, that's our surrounding. So I also try to use this example to tell you, look at my original equation. I don't produce water at all, right? Okay, but then again, majority of that solvent is water. So again, the surrounding is water. So then I gather information for water, then I know they have an opposite relationship to my reaction. Then I can find information about my reaction from that point. Okay, so then that's just something I want to remind you about. Okay, so make sure you have a clear idea about this type of question, and then hopefully this is helpful, and thank you for listening.